Hi, everyone, and welcome back to GLG 171. In this lecture series, I'm going to cover volcanoes and volcanic hazards. In the first lecture, I'll discuss the different types of volcanoes that we find around the Earth and the plate tectonic settings that explain their locations. In order to understand volcanoes, we first have to look at the sources of volcanic material, which is magma. Magma, which is typically called lava when it reaches the surface, forms from the melting of rocks deep beneath the Earth's surface. So typical depths for melting would be somewhere in the order of 50 to 250 kilometers. It is the source of the magma and partly the rock that it ends up migrating through that determine the type of volcano that will form at the surface. Different rock types melt at different temperatures, as we learned in the lecture on igneous rocks. However, those temperatures are more easily reached at depth due to the geothermal gradient. That is, the fact that the deeper you delve into the Earth, the higher the temperature is. Volcanoes are not random and are formed predominantly at convergent and divergent plate boundaries. However, much like earthquakes, there are some volcanic centers that appear far from the plate boundaries. These are known as hotspot volcanoes, and they arise from superheated portions of the Earth's core and mantle. This localized increase in temperature forms a column of molten rock known as a plume that develops into a flood basalt when it reaches the Earth's surface. Volcanologists have very exciting, we'll say, jobs. For those who do research on active volcanoes, taking lava samples is a regular event for most of these. For the most part, these images are of students taking samples, and the only individual that is actually prepared in safety attire and has appropriate sampling technique is the one in the lower left-hand corner. She's actually prepared for the heat of the magma that she's actually sampling. The other ones are taking localized samples that could be used for actual research, but are probably for a field trip or a class. The lava samples that they're collecting would be quickly drenched in a bucket of water, and the resulting obsidian-like rock could be analyzed to determine the geochemistry of the flow, types of magma that are forming from it, and any changes that occur could warn you about an imminent eruption. So they're not normally taking these samples for no reason, considering how dangerous they can be. The majority of Earth's volcanoes are located along what is called the Pacific Ring of Fire. It's a pattern of volcanic activity that you can see traced around the Pacific Ocean. Those volcanoes are the result of subduction of the Pacific Plate under the surrounding continental plates. So the overriding continental plate is then subjected to the resulting magma that forms as the subducted plate partially melts. In each case, the chemistry of the magma that forms is a function of what minerals melted during the process. If lower temperatures dominate, then felsic mineral magmas will form. If the temperature is intermediate, then we have intermediate magmas as a result. And if high temperatures allow more complete melting of the mafic ocean crust, then mafic magmas will dominate. We'll see those magmas are what determine the chemistry and physicality of the volcano that forms over the structure. The magma viscosity is probably the most important characteristic of magma that we can look at. The temperature and chemistry of the magma determine its viscosity, and viscosity is a resistance to flow. Peanut butter has a higher viscosity than honey, but not as high as, say, cold tar, which is capable of flowing. Solid glass is actually not a solid and has a viscosity that's extremely high, but will flow over centuries. In general, the more resistant a magma is to flow, the more pressure will be required to erupt it at the surface, and therefore, the more violent the volcanic activity will be. Felsic magmas have high silica content, and silica has a sticky texture to it, so that high amounts of silica, high amounts of gas, and low temperatures result in the most violent types of volcanoes. Mafic magmas have the lowest silica content, the lowest gas content, and the highest temperatures. And gas plays an important role because the more gas you have trapped in the magma, the more it will expand when it reaches the surface and depressurizes, thus aiding the violence of the volcano. So low temperature, high gas, high silica, really violent volcanoes will form. If you have high temperatures, low silica, and low gas content, then relatively quiet volcanic eruptions are what we would be looking for. So these quiet eruptions are still devastating, but they're mostly dominated by lava flows, and they don't destroy the entire mountain every time they erupt. We typically see frequent small eruptions at these locations. So every little bit of increase in pressure creates a new eruption, and they don't build up to catastrophic amounts of pressure. So at large eruptions, places where we have felsic magma, then these are very infrequent, and the pressure builds up to high amounts, and we end up having very catastrophic eruptions of those volcanoes, sometimes destroying the entire mountain itself. The sources of magma are really what's important. So if you have a mafic magma, then that tends to be what will produce basaltic style lava flows, or if it hardens beneath the surface, that we call that gabbro. If you have intermediate magmas, they produce andesitic lavas, or what would be called a diorite if it formed in the plutonic region. And then felsic magmas, which produce rhyolitic lavas. And those, the equivalent to that would be granite in the subsurface. So violent volcanoes, you would expect to find more rhyolitic and andesitic lavas. And then quiet volcanoes, you would expect to find basaltic lavas that are present. Because of that, we would anticipate that a quiet volcano, such as an example would be Hawaii, has low viscosity, basaltic lava, mostly lava as the hazard, and has very frequent eruptions every decade to every century. Violent volcanoes have a very high viscosity. They have felsic style to intermediate style lavas. They're infrequent eruptions, meaning every few hundred to every few thousand years, sometimes on the order of tens of thousands of years between eruptions. And the types of hazards are very diverse. So lava is still present, but we also have ash flow, lahars, landslides, tsunamis, those kinds of things are the result of very violent eruptions. If we looked at a mafic style eruption, then we would expect to have predominantly lava. So even though this lava could be produced at a felsic style eruption, I'm going to cover it here. Lava flows, which are dominant in our mafic environments, can be broken into two basic categories. If they are very ropey and have a smooth texture, as is in the image in the upper picture here, then that would be considered what's known as a pahoehoe lava. And these words are derived from Hawaiian terms that have been used for millennia to describe the lava flows. A'a lava is rough and jagged blocks. So in the bottom image, just above my head and behind me here, is an a'a lava flow, where it has cooled and has broken up into big chunks of already cooled material with a molten core. Those tend to be very slow moving, so that you could walk in front of this type of lava flow. Whereas a quick moving pahoehoe lava flow would actually be very difficult to stay in front of, and tend to be the more dangerous types of flows in places like Hawaii. But these hazards are easily seen in some of the locations that would you'd be able to visit in Hawaii. If you can't get your worldly goods out of the way, then things like vehicles are trapped beneath the lava. And if you have a roadway that's inundated by basaltic lava flow, or homes or villages, then they're inundated with material that is very difficult to remove. It's not like mud after a flood. That's difficult to remove, but able to be cleaned off. In this case, you have solid rock that forms around the location where the lava flow occurred. The materials in a violent volcanic eruption are, we do still have lava, but also we have what are called pyroclastic materials. And pyroclastic means fiery fragments. And this includes things like ash and dust, really fine particulate matter that is very different from the modern day dust that you would think of that falls in your house or lands on an undusted shelf. You can have larger pieces of what are called pumice. That's that volcanic glass that we talked about in the volcanic rocks chapter. And then we define them by size. So if you have big pieces, they're called lapilli. Cinders are pea-sized. And then particles that are larger than lapilli can be called blocks or bombs. And these volcanic blocks and bombs can be relatively large. Blocks can be the size of a car or a house if they're blown out of a large eruptive vent. And this volcanic bomb in the image is about 10 centimeters long, and it cooled in the air, you can tell, because it has an aerodynamic shape to it. So it takes on a sort of teardrop shape or raindrop shape that we expect. The ash just above me here is volcanic ash. It's made of silica. It's extremely porous, made of silica, so it's rough and locks together quite tightly. So when you have large amounts of volcanic ash that forms in inches to feet of deposition in an area, it can be absolutely devastating. It's not like snow, it's extremely dense, and that means that it can crush roofs and destroy vehicles. It is abrasive because it's made of silica and has lots of edges. So if a pilot were flying through a volcanic ash cloud and didn't know it, couldn't distinguish it from a regular cloud, then the silica would gum up the engines, and there are cases of jet engines flaring out because of volcanic ash. I've never seen the report of a commercial jet or otherwise crashing as a result of volcanic ash cloud, but there are transcripts of discussions between a pilot and the tower when they've flown through a volcanic ash cloud, when the engines failed and they plummeted out of the sky for a short period of time. And then once they cleared the cloud, they were able to get the jets going and land themselves safely after diverting the flight. So volcanic ash is not like typical fiery ash that forms from the burning of wood. In this case, it has much different characteristics and can be devastating. In the case of a volcano, regardless of what type we're talking about, violent or quiet, there are a few different general features that we would tend to look at or analyze. There's a conduit, which is the pipeline from the magma source down below that carries the magma to the surface where it's erupted. There's the vent, which is the opening of the conduit at the surface, and that usually is found within the crater. So there's a steep walled depression at the top of any given volcano that we would call a crater. If it is larger than a kilometer in diameter, it gets the special term caldera. And some calderas can be tens of kilometers in diameter. I'll give you examples of those later in the lecture. When we look at volcanoes, we break them up into certain types, certain categories. And in general, the categories that we use are flood basalts. These are the initiation of a mantle plume. When the plume of material hits the surface, it erupts in large volumes and can form vast areas of regions that are covered by basalt. Second in size to that would be shield volcanoes. Those form in areas that result after a hotspot has occurred, and they're continually sourced by magma, usually mafic magma, that allows them to form a large but low angle volcanic vent over the top. Cinder cones are short-lived and usually erupt 2 or 3 times before they're completely spent, and they may be on the order of 200 or 300 feet high and are typically found around and adjacent to larger scale volcanic events. Composite cones, or stratovolcanoes, are the types of volcanoes that people think of when you use the word volcano. So Mount Baker, Mount Hood in the Pacific Northwest. Those are examples of very viscous, very violent style eruptions. And then volcanic domes are the resulting dome that can occur after an eruption has already occurred. They're small in stature and may form within the interior of a larger eruption. And the very last characteristic is a caldera eruption. These are the largest eruptions and distribute material over hundreds of square miles, sometimes thousands. And they form the collapse of the volcano itself from an eruption material, and I'll cover those last. The fissure-style eruptions, or flood basalts, form when you have a large amount of basaltic material that is erupted through fractures in the Earth's crust known as fissures. There's no centralized volcanic activity here. In this case, you have fissures that can be hundreds or thousands of kilometers long that erupt material at the Earth's surface. In the case of the United States, we have a good example of the Columbia River basalts. As you can see in the upper left-hand corner up here, the Columbia River basalts cover a good portion of the southwest corner of Washington and the northeast corner of Oregon and parts of Idaho. This volcanic plateau is formed from a plume that cut through the North American continent, and then the mantle plume itself that is left over is now forming the volcanic rocks you see in the Snake River Plain and result in the volcanic activity that's still present in modern-day Yellowstone National Park. Shield volcanoes, which are relatively large, slightly domed, mostly basaltic sourced volcanoes, are exemplified by something like Mauna Loa in Hawaii. It's a very large mountain. If we count the distance of the from the crust to the surface of the water where Mauna Loa actually peaks, then the island itself isn't very high, but it stands very tall off of the ocean crust. So it is a really big mountain, one of the largest present on the Earth today. It's sourced by basaltic magma, and the reason that it has such a large size is that as the magma flows out, it's low viscosity, so it makes relatively level layers, and they build up through time to form a broad, low-sloped but massive volcano. The Big Island of Hawaii, which is typically what we think of when we think of Hawaii, is actually formed of 5 different shield volcanoes that have sutured together and grown on top of each other or adjacent to each other over the millennia, over the last 5 million years. And then each island in the Hawaiian island chain is a shield volcano or shield volcanoes that have sutured together in the past, getting older towards the northwest. Stratovolcanoes or composite volcanoes are what we typically think of when we think of volcanoes themselves. They're adjacent to the Pacific Ocean, found predominantly on continental land masses, but they can comprise volcanic island arcs as well. Japan is a good example of a stratovolcano in Mount Fuji and some of the other active volcanoes in the island chain there, and in the Philippines, the same. In the Pacific Northwest, we have Mount Rainier and Mount Hood, and of course, Mount St. Helens, which actually erupted. And we'll talk about that in the next few slides. These are large in size, and instead of just being predominantly lava, they're made of interbedded lavas and pyroclastic materials. They're extremely violent in their eruptions. You can see behind me, or above me, the erupting volcanic cloud that's generating lightning strikes because of the static electricity that's formed between the different ash particles that are moving together in the atmosphere. Mount St. Helens is a fantastic example of a shield volcano, or of a stratovolcano, composite volcano. It has nice steep sides. It's relatively large in its size, but not as big as a shield volcano. And if we were to drill down through, we see alternating layers of lava with interbedded pyroclastic materials. In May 1980, Mount St. Helens erupted. It was being monitored by geologists because there was a swarm of seismic activity that had occurred, and the mountain was experiencing what is called tilting or swelling. The north face in particular, which is what we're looking at in this image, was bulging out 200 or 300 feet in elevation towards Spirit Lake, which is the lake in the foreground here. Mount St. Helens, on the morning of May 18th, 1980, experienced one of the largest continental eruptions to occur in modern human history. The material was freed up when a landslide, the bulging side of the mountain, slid off and into the area where the lake was pre-existing to the eruption. That released pressure off of the material underneath, which had been building up for centuries, and the eruption blasted northward. It was a lateral blast. That was unexpected. Most geologists at the time imagined volcanoes and envisioned volcanoes to be erupting vertically. So what happened was, because the north face of the volcano was bulging, we had a geologist stationed to the north of the area. He had time, his name was David Johnston, and he had time to radio in Vancouver, this is it. That was the base station for the volcanic monitoring. They had evacuated the area, and 57 people had died that were in the area. They were either scientists that were in monitoring the volcano because a general evacuation order had been in place, but there were some locals that would refuse to evacuate and were effectively buried in their homes by the landslide and the subsequent eruption. The remnant eruption, what occurred after the lateral blast, was more traditional in that you had a vertical column of material moving 20 or 30,000 feet into the sky. And the mountain itself, as you can see behind me, lost about 1,300 feet in elevation, the old peak down to the valley of the crater beneath. It very quickly, over the next few years, built a resurgent dome or a volcanic dome. And you can see that in the small-scale eruption that's occurring here in the image from the 1980s on the right-hand side. Composite cones have a number of different hazards that we don't see present in other volcanoes because they build up so much pressure and because of the high silica and gas content, they can produce things called nuées ardentes or fiery clouds. This is a superheated cloud of pyroclastic material and hot gases that can be on the order of 200 or 300 up to 700 degrees Celsius on the inside. They flow down the side of the volcano. They superheat the layer of gas underneath them so that they are effectively moving frictionless, and they can travel at upwards of 100 to 125 miles an hour down a valley side. These are absolutely devastating when they occur, although they are infrequent. They don't occur with every volcanic eruption. The most devastating volcanic hazard that we'll see is what's called a lahar. A lahar is a volcanic mudflow. You have a bunch of ice on the top of a volcano if it's if it has a high enough elevation or is it high enough in latitude. And that ice combines with the ash that's being erupted. There's also rain that forms as nucleation sites because of the eruption that's occurring. And it mixes with the soil from the volcano, the ash that's being produced, and forms a mud flow. Don't think of this like a flood. The wall of material that's moving down is extremely dense. It would be like being inundated by concrete. Lahars are extremely devastating. But the nuées ardentes are the ones that sort of capture movie history and the general public's interest. A good example or a bad example of a nuées ardente would be the island of Saint Pierre, the city of Saint Pierre, which is on the island of Martinique. And the island itself is actually produced by the volcanic center of Mount Pelée. So in the distance there, you can see Mount Pelée. And then in the image before the eruption, this is the main city on Martinique called Saint Pierre, the capital. On the evening in 1902, the volcano began to rumble, and actually for days ahead of time, it had been giving warning. And when the eruption took place that evening, a nuées ardente spilled down the valley into the bay where St. Pierre was located. There were a handful of survivors, many of which did not live for very long afterwards because the pyroclastic cloud absolutely demolished the town. What you are seeing here are the remnant walls of the buildings and structures that remain standing after the lateral blast, or after the pyroclastic blast moved through the city. Similar structures have been seen in Hiroshima and Nagasaki after the dropping of nuclear weapons on Japan in World War II. So the survivors that did make it, one of which was on a boat, and another one was a prisoner in a cell. He had gotten into an altercation the night before and was in a prison cell, which happened to be partially underground and was of sort of high safety. So it was thick walled, and there was a little gap underneath the door. You can see that in the destructive image on my right here, and then above me is the cell that he was actually found in. He survived because he was in that cell. He urinated on his clothing and stuffed it under the vent to keep the gases from coming in. He was still badly burned because this effectively turned into an oven, but he was able to survive and then went on to travel with Barnum and Bailey and talk about the devastation that he lived through, because effectively 30,000 other people were killed during this eruption when the nuées ardentes swept through. And he was one of very few survivors to actually witness it, although in this case, he didn't get to see any of the nuées ardentes because he was protected by the prison he was in. The most devastating occurrence that can happen during a volcanic eruption, a composite cone volcanic eruption, is a lahar. These are volcanic mud flows. The hillside that you're seeing in the image back here that is brown was erupted during a volcanic flow. Mud formed from rain and melted ice, soil, and ash debris form these thick, soupy, concrete-like rivers that pour out of the volcano and down slopes. So you're safe from them if you're high enough in elevation, and you are at risk of being inundated by them if you're in a river valley. When Mount St. Helens erupted, it filled the Toutle River and surrounding river valleys with vast amounts of material. The mud in this case flows through, and because it's so dense, it can pick up things that normally floods wouldn't pick up, like, for example, houses here, and move that house off of its foundation. And then when it stops moving, the water drains out, but the mud is still solid. So it's not as difficult to get rid of as, say, volcanic rock like you would find in Hawaii, but it is not something that you can preserve a home from like you could just simple floodwaters. So these lahars are extremely dangerous because they happen all the time and they fill up river valleys, which is where people tend to congregate and live when they live around a volcano. There's one more extreme case of a volcanic hazard that can occur predominantly at the composite cone style, but this could occur at a shield volcano as well. In tropical regions where you don't get ice at the top of a mountain, the crater can be filled with water. And there are cases of that water storing large amounts of CO2 that is being erupted from the vent underneath it, much to the chagrin of the people who live in the area. Like an opened bottle of soda, if you remove the pressure by either disturbing the lake during an earthquake or stirring the water because of fall overturn when temperatures change, you can bubble that CO2 out in one catastrophic destabilization. It's nice and concentrated in the deep water beneath the lake when it's cold. And then if I shake it, it bubbles out. That CO2 is denser than air, so it rides down the valley floor and makes it to places where people live. In this case, an example of that would be Lake Nyos in Cameroon, West Africa. And the CO2 traveled through in the middle of the night, and people and livestock suffocated because obviously you can't breathe just CO2, and they just didn't wake up. So about 1,700 people and countless heads of cattle and wild animals were killed by this belch of CO2 from the volcano. In order to prevent this from happening in the future and in other locations where the volcanic activity is similar, they drive vents down into the bottom and they try to slowly release the CO2 as it's being built up so that it can't reach catastrophic levels. You might wonder at this point, why do people live near volcanoes? Well, in the case of places like Saint Pierre and Montserrat, those places are beautiful and the islands are lush and tropical and they have fertile grounds. So they are very appealing. The mountain scenery, the local tropical setting, the beautiful mountains like Fuji in the background if you're living in Japan, or having Mount Hood or Mount Rainier in your background for recreational purposes in the Pacific Northwest is very appealing. They're spectacular sources of things like metal deposits and solid debris, pumice and ash we mine. They make really fertile agricultural lands. The ash and volcanic rocks degrade into very good soils. So there are lots and lots of benefits to living around a volcano, but in order to safely do so, you have to know the hazards and you have to be able to take some mitigating steps to protect yourself. And that will be something that we talk about in the next lecture in this series. I've saved the worst for last. The most violent types of volcanic eruptions are called caldera eruptions. A good example of that would be Crater Lake in Oregon. It was formed by the collapse of a volcanic mountain. What happens is the volcanic eruption is so violent that the entire mountain itself is destroyed, and then a subsequent bit of volcanic activity can produce a small parasitic dome, an eruptive dome, like Wizard Island in the middle of Crater Lake that you're seeing in the image. The size of the collapsed volcanic structure must be more than a kilometer to be called a caldera. But in the case of Crater Lake, the series of events that leads to the formation is you have an ancient volcanic mountain called Mount Mazama. And the eruption of the mountain, which is recorded in native tellings, we see it in the writings and histories of Native Americans. Mount Mazama erupts with such violent activity that in the image on the left-hand, on the bottom image, on the left-hand side of your screen, the chamber itself is emptied. Well, it's holding up a mountain, so that empty space can't exist. And as it's erupting all of this volcanic material, the mountain collapses down into the void space, and you end up with a gigantic volcanic crater, which can then squeeze out a last little bit of magma material to form the dome like Wizard Island. These eruptions can be massive, and the calderas themselves can be massive. We have our own series of 1.7 billion year old volcanic calderas in Missouri. If you take a field trip out to Elephant Rocks, that's the magma chamber. But the Tomsock area has a caldera that's about 14 kilometers across. So the students here are standing on one of the rim granites, and off in the distance, you can see the hillside that is present there. They are looking at, it's about 14 kilometers away, and the valley beneath is the floor of the caldera itself. That eruption was spectacular, but it would have been 1.7 billion years ago, and there's no risk of volcanic activity occurring in the future. In modern times, these caldera eruptions constitute the largest eruptive features that we see on the planet Earth. The biggest one that we have record of in relatively modern times is 28 million years ago, the La Garita caldera in Colorado, which erupted 5,000 cubic kilometers of material, tuff, which is a mixture of volcanic pyroclastics that forms a rock. The second to that was the Toba caldera in Sumatra in Indonesia, which erupted about 2,800 cubic kilometers of material, and the eruption occurred in the last 2 million years or so. More recently than that, we have the Yellowstone caldera, which has erupted 2 million years ago, 1.2 million years ago, and 0.6 million years ago. And those eruptions covered good sections of the Rocky Mountain region all the way out as far as Missouri. We've actually recovered some of the Huckleberry Ridge tuff that has been present, that was preserved in one of the caves just south of Springfield River Bluff Cave. So these eruptions are catastrophic when they occur. You can imagine if an eruption at Yellowstone occurred today, the ashfall would cover up good portions of the North American agricultural fields of the Midwest, and that would be devastating to modern day human populations. However, even though it looks like they occur regularly about every 600 million or 600,000 years or so, in reality, there's anywhere between 1 million to 500,000 years between them, and that means that there's a lot of wiggle room between the last eruption and this eruption. We do constantly monitor the Yellowstone caldera, but it's very unlikely that it would erupt at any given time in modern human history. As far as mitigation goes, there isn't much you can do to mitigate the hazards. So you would attempt to survive and do what you could after one of these eruptions took place, but they're not going to be covered in the volcanic mitigation chapter that you should watch after this. So that's what I had for volcanic eruptions. Thank you for listening, and I'll see you in the next lecture.